Today, we are going to talk about balance. Okay, balance. What does that look like in an atom? And you're actually going to have an opportunity to do some of this on the computer on Thursday. Okay, but until then, we need to talk about kind of the idea behind it. So what you see before you is an atom. That's a nucleus in the center. This is not to scale. Okay, this is not really how an atom looks. This is just for learning purposes. Okay? In theory, the nucleus is incredibly small, and the electrons are really far apart. Okay, but we don't have the luxury of looking at it quite that way when we're trying to understand how it works. So, disclaimer, this is not to scale. All right, now, we have protons, we have electrons, we have neutrons. Okay, can anyone tell me, based on just my diagram, what atom this is? And how do you know? Mary. B. E. B. All that you can be. I will be there for, there's a key, for you. Okay? Beryllium. And how did you know? There are, oh, beautiful. There are 4, count them, 1, 2, 3, 4 protons in the nucleus. The protons identify the atom. You will be required to do this for numerous atoms. And we'll give you numerous diagrams, and you have to tell me which atom you're looking at based on the nucleus. This, you should be able to, yeah, I could give you any one of them on the periodic table, and you'd have to count the protons. Do you want 91? Because I could do that one. No, that's a nice one.
Just don't do 8 for new.
103? Yeah, All right, so here's what we have going on. We have a beryllium atom. And right now, there are 4 protons. What is the total charge, then, if we have 4 protons on the positive end of things? What would we say? Erica? Plus 4. And we have 4 electrons. So those are negative particles. So -1 plus -1 plus -1 plus -1 adds up to -4. Mary? It would not. You just said it yourself. There would be how many protons? You said 5 protons. 5 protons means you've added a proton and changed the identity of the atom.
But does
the electrons do matter, but it first depends on which atom you're working with. So, yes, you could have an atom like that. Boron would be the one you'd be working with, though, not beryllium, because it has 5 protons. Okay, and then carbon has 6 protons. So if I were working with 6 protons, I'd be working with a carbon atom. Okay, so if we were to add or subtract protons, that changes the element we're working with. But we can get positive or negative by just working with electrons, and that's what we're going to look at today. So I have 4 protons plus 4. I have 4 electrons minus 4. So right now, what is the total charge on my atom? Chloe? 0. When the total charge equals 0, we call this a neutral atom. A neutral atom. And this can happen for any atom. Hydrogen, 1 proton, 1 electron. It's neutral. Lithium, 3 protons, 3 electrons, neutral, okay? Scandium, 21 protons, 21 electrons, neutral. Potassium, 19 protons, 19 electrons, neutral. Every atom can be neutral. And some like that, okay? I'm not saying they all do. Like some of these atoms over here, they don't like to be neutral. The ones on the left-hand side of the periodic table, they don't. So you're going to actually see them do things to become unbalanced. And we'll look at that. But see, these ones on the far right, helium, neon, argon, krypton, radon, xenon, these elements, they love being neutral. As a matter of fact, helium and neon are only neutral. That's all they are. They're super stable elements. Yeah.
So if there were more than four, like say there were like 8 electrons, would it still be beryllium?
In this particular example, it doesn't matter if I had 1,000,000 electrons. If I have 4 protons, it's beryllium. It doesn't matter what's in the nucleus, the protons determine the element. If there was no electrons, it'd be beryllium. If there were 6 electrons, it'd be beryllium. If it was 8 electrons, it would still be beryllium. The moment you add or take away a proton, it's no longer beryllium.
Man, I love that drawing of your atom.
That is just a temporary setback. Okay, so that's what we're dealing with here. Okay, 4 protons, 4 electrons, total charge is 0. This is a neutral atom. Now, let's take a look at, I'm going to copy this slide. Okay, and if you can't copy it, that's fine. Hang on. I'm copying this. Okay, here we go. So it doesn't look like anything changed, but we're actually on a new page. I'm going to go ahead and just erase these numbers. I'm going to leave the protons, electrons there, total charge, and I'm going to get rid of this neutral atom. Okay, so I'm going to look at a new atom. What would happen, do you think, if I had an electron, I'm going to put it down here, that decided to leave? Okay, it's gone. All right, it's gone. So it went from being there to being gone, okay? I'm going to put it in the little penalty box. It's no longer with us. It's in timeout, that's right. All right, what would happen here to this penalty box? What's going to happen to my charge? Let's count it up. How many protons? Guys, really? How many protons?
3.
Protons. 4. So we're still at plus 4 in the nucleus. How about electrons? Mary? 3, which means we're going to have a negative 3 charge. What's my total charge, Caitlin? Yes. When this happens, and there is an unbalance, what? Then we would say we no longer have a neutral atom. We have something called an ion. An ion. That's what we're working with. It's an ion. We're not talking about the car, the ion. Okay? Tiny little car it is. There is. The ion. All right. Is there other ways to get ions? Could we get a different charge? Let's say not -1. Someone throw out an idea. There's multiple ways to do this. What could we do? Mary? Could have 3 protons, but let's keep 4 protons. Let's not touch the protons. Let's just work with the electrons. You know, I think the flower is just feeling awfully vain today. Okay, let's try this again. Okay, Mary, how could I go about adding or subtracting or doing something to create a different charge than +1? I'm not going to touch the protons. What could I do?
You could have 5 electrons.
I could have 5 electrons. Okay, so we got to take out the penalty box and reinstate said electron. Okay, I'm going to move it back down so you see it pop up. And then I'm going to add another. I now have 5 electrons, 5 of them. So, change my numbers up a little bit. 5 electrons. This would be -5. What's my charge going to be? Okay, it's going to be -1. Still an ion. Still an ion. Okay, definitely. What about if I added another electron? Okay, now I'm at 6 electrons. What charge is that going to give me? Anna? Well, you're right overall, but if I have 6 electrons, that's a total of negative what? 6 in the negative department. Okay, I want to fill it in right here. And that gives me an overall, you're right, Anna, -2 charge. -2. We're going to change it several.
When it's not 0, it's an ion.
When it's not, yes, that's exactly what we're talking about here. When the charge on the atom, Mr. Hogel, is not 0, it's an ion. That's important. Ions are what allow our body to function. Okay, you've ever heard of electrolytes? You have to drink Gatorade and water to keep up your electrolytes because you're sweating a lot in a sports game. That's based on ions. Okay? Your nervous system relies on sodium and potassium ions in order to communicate between your brain and your muscles. Without those 2 elements, sodium, potassium, and a few other things in your nervous system, your body would cease to function because your brain could no longer communicate with the rest of your body. So ions are incredibly important. Incredibly important. Especially for your just daily operation. Yeah.
Why is it so important to have something that's unbalanced rather than balanced?
Because it's the way that it interacts with its environment, right? And I'll give you an example of this. A magnet. Is a magnet useful?
Yes.
No.
Magnets
Yes.
are incredibly useful, right? They're unbalanced. They have north and south poles, right? Like an atom, they have positive and negative charges. Magnets are not balanced. If they were, they'd have no magnetism. But everything in here is facing either north or south. It is unbalanced. Okay, so magnets don't have necessarily all of the same thing or whatnot, and yet they're useful to us. All right, they're useful to us. Same thing with ions. All right, if you have a positive and a negative ion, they come together. What are they going to do you think? Think about this. Hannah, Caitlin, Millie, Gretchen, Katie, Mackenzie, Austin, Noah Hogel, the rest of you. Think about this. If you have a positive and a negative ion, what do you think they're going to do?
Repel.
You think they're going to repel? That's his guess.
Attract.
You think they're going to attract. Why, Colby?
Because they're opposite charges.
They're opposite charges. Do you enjoy table salt? Do you enjoy table salt? Yeah, table salt. Did you know table salt is a positive sodium ion and a negative chlorine ion? And because they were ions, they can form a bond, and that bond makes table salt. You wouldn't want them by themselves. Sodium by itself is incredibly explosive when it comes in contact with water. If you were to eat it, being about 90-some% water yourself, it would blow a hole in you. And then there's chlorine, and chlorine is so corrosive, it wants to bond with something so bad that it would rip apart the water in your lungs, creating hydrochloric acid, which would dissolve your interior organs. So you don't want to have just sodium, you don't want to have just chlorine, but because they can create ions and bond, which we're going to talk more about, they create table salt, which is a delectable spice that we can put on our food. It's delicious. Yes, Mary.
That's just called stupidity.
If like sodium has, I know this isn't right, but it like has like 4 protons, and
Has 11. Continue.
Okay. It has like 11 protons and then 10 electrons or whatever.
Yes.
And then if
Which is exactly how it forms an ion, by the way.
chlorine or whatever has the opposite amount, would it like all match up each of them so that they could like and each one with the positive match up with the negative?
That's exactly it, Mary. That's exactly what they do. Sodium has a +1. It needs an electron to be balanced. Chlorine is -1. It has one too many electrons. It's trying to either balance out or get rid of. So what happens is sodium needs one, chlorine has one. They have a relationship. And so they bond. Chlorine fulfills sodium's needs, sodium fulfills chlorine's needs, and they form this wonderful thing called table salt, which is fantastic. Yep. No. No, it's kind of like a marriage, right? It's kind of like a marriage. Yep. Absolutely. So that's what's happening here. Now, there are, go ahead and take a look at your notes because we're going to try to finish this out here. There are 3 variations for atoms. And while this is going to be mostly review, I'm introducing yet one new idea here at the very end. Neutral atoms have a balance of protons and electrons. That's why we call them neutral. And you should know that even though neutrality is important, most elements are not happy in the neutral state. They're just not. Okay? For some reason or another, they're not happy. We'll talk more about the happiness of atoms next week. But for now, you should understand that while neutral, most of them are, most every element is neutral. They don't necessarily like that. Then we talked about this idea of an ion. Ions are unbalanced atoms that have either a proton in the nucleus that's unbalanced or extra electrons. Okay? If it has more protons, obviously, than electrons, it's positive because you have more of those positive charges in the nucleus that are unbalanced. But if you have a lot more electrons, or even one more electron that's unbalanced, then it's negative. So it really depends on whether you have too few electrons or too many electrons. Most atoms like forming ions because they become more happy in that state. Yes, more happy. So ions actually fulfill a need for most atoms. We'll talk about why that is, Mary, as we continue in just a little bit. Then last but not least, there is this thing, and this is new to you, called isotopes. And isotopes are what we would say are different versions of the same element. Okay, different versions of the same element. Okay, I'm going to give you some examples of this in real life, in the universe. Hydrogen. Okay, hydrogen has one proton, and typically speaking, that's fine, has one proton, and typically speaking, it has one electron. Okay, hydrogen, one proton, one electron. That's really important for our understanding of what's happening here. But in nature, hydrogen has multiple atoms with different numbers of neutrons. Okay, gentlemen? What did I just say?
Different numbers of electrons and neutrons.
I'm going to quiz you at the end. You better have all the right answers, or you can't bring that anymore. So, protons and neutrons, electrons. Isotopes have different numbers of electrons. See, what scientists have done is they have canvassed the universe. They have studied stars. They have studied space matter. They have studied our own Earth, mostly our crust, magma, etc. And what they have found is that these elements on the periodic table have different versions of themselves. Hydrogen happens to have 3 or 4 different versions, and we give them names, okay? We give them names like tritium and deuterium. These are different variations on hydrogen. Okay, what would make them still hydrogen? What particle makes them hydrogen? Yeah, the one proton. So what we do is we look for elements that have one proton, atoms that have one proton, and then we study the nucleus. We weigh the nucleus. We can do this. This is kind of cool. We weigh it, and we realize, they're not all the same. Some nucleuses are a little heavier than others, but we know their proton is one. We know that because it's hydrogen. So the only explanation, there must be different numbers of neutrons. So what we would say is, on the screen here, look, we have three different atoms. We have a proton-electron pair. We have a proton-neutron-electron pair. And over here, we have a proton-neutron, no electron pair. Okay? These are all hydrogen. Why? Colby. They have one proton, but they're all different. Okay? They're all different. So let's go ahead and break this down and see if we can identify what each one is. This first one has one electron, one proton, and 0 neutrons. So is this a neutral atom, an ion, or an isotope? Mary? It is a neutral atom because there is an equal number of protons and electrons. Very good. What a neutron does is it creates what we call stability. Okay, it creates stability. So if we add neutrons, or if some elements have different numbers of neutrons, what would happen is that actually determines their radioactivity. Iodine, right up here in the periodic table, iodine. There are a lot of different versions of iodine. Some of them are radioactive and some aren't. And it depends on how many neutrons they have. Okay, cesium, same way. Cesium, they actually use this in cancer treatments, okay, to isolate and kill tumors. Cesium, there are different versions of it. One of them's really effective because it's so radioactive at killing cancer. But some of the other ones, not effective at all because they're not radioactive. There are different versions, but it doesn't mean that they're not cesium. They would still have 55 protons. And oftentimes they still have the same number of electrons. They just have a different number of neutrons. So really it kind of determines their stability, their radioactivity. That's kind of what neutrons determine. Okay, and that kind of is where this idea of isotopes comes from. So we have one electron, one proton, 0 neutrons. The next one, we have how many electrons? How many? Yeah, thank you. It's not rocket science. There's one green dot. One electron. How many protons? One proton. It'll show up. Ah, there it is. And how many neutrons? One neutron. Okay, so that means it has a different number of neutrons. Is it still balanced? Is it still relatively neutral? Yeah, so what we'd call is this a neutral isotope. It's a neutral isotope. What about the last one? What about the last one? Gretchen Rainey, try it. All right, Gretchen, I'll ask you a question. Is it balanced? Does it have an equal number of protons and electrons? Yes. Okay, so there's how many electrons here? 0. Okay, how many protons? 1. Okay, so I'm going to write that down. There is 0 electrons. There's 1 proton, and how many neutrons, Gretchen Rainey? 1 neutron, fantastic. Okay, is it balanced? Does it have, because balanced means it's neutral, equal numbers of protons and electrons? Equal? Nope. Nope, definitely not. So, very good. It is not neutral, but, so that makes it what? A what? Think about the unbalanced. Okay, it's really going to be neutral or ion. It's an ion, and it does have an neutron, which is different than the first one. So we would call this an ion isotope. Exactly. That would actually be a perfect summary for today's notes. Yes. Because it's better when you guys say it. It's actually fantastic.
Can't they just tell us to say it?
Is there like a certain name for the first one?
First one, hydrogen. They do have special names. Real quick, I'll come back to this. But basically, if we were to go to Safari here, and we were to look up isotopes of hydrogen, protium, deuterium, and tritium. Look at it right there. So protium, it consists of 1 proton, 1 electron. Deuterium consists of 1 proton, 1 neutron, 1 electron. Tritium is a hydrogen isotope consisting of 1 proton, 2 neutrons, and 1 electron. So what we had there was protium, deuterium, and tritium in our examples. Okay, these are isotopes of hydrogen. Which one is the most abundant based on this right here? Mackenzie. Protium. Protium is 99.98% of all hydrogen that we are aware of, which means all the hydrogen in the universe, which includes our sun and all stars that we can analyze, which includes countless millions and billions of stars. Okay? Any questions about this? All right, let's go ahead and stop this recording. And then what we're going to do is talk about what this week is going to look like again.